Everybody- Is everybody satisfied with their search experiences this morning? I know that's an interesting question conceptually, but I'll ask it a different way. Have people managed to actually do the searches mechanically so that they're getting output that sort of makes sense, and can they get control over how to put background knowledge in, et cetera? All that's working, right? So you're getting a grip on what that is to do? Great, okay. Okay, so I'm going to back up and I'm going to tell you a little bit of the theory of search, and then we're going to go into deseparation and get out the other side before lunch with hopefully some real understanding of what's driving a lot of these search algorithms and a lot of the theory behind what causal models predict about data. So the first thing to say is that the search space that we're actually dealing with in this set of problems is extremely large, right? If I just said, let's just search for all the directed graphs out there instead of just the patterns, right? Then the number of graphs that I'd be searching is between 2 to the n choose 2 and 3 to the n choose 2. And the reason it's between 2 and 3 is the usual way to think of these things is between every pair of variables, right, there can be an edge one way or the other way or not at all. That's 3 possibilities, and the number of pairs of variables is what you raise that to a power of, right? So it's 3 to the n choose 2. And n choose 2 is the order of n squared. So the upper bound on the number of graphs is 3, right, to the order of n squared. But you don't need 3 because in many cases you'll have cycles. And we're looking at directed acyclic graphs. So sometimes there are only 2 possibilities for an edge, non-edge, or the one way. So that's the lower bound. So it's in between 2 to the n choose 2 and 3 to the n choose 2. And since n choose 2 is order n squared, not a big difference there. It's super exponential. It grows extremely fast and is virtually impossible to search exhaustively even when you have 30 or 40 variables. So the number of directed graphs, which includes cycles, right, is 4 to the n choose 2 because between every pair I could have one way, the other way, 0, or both ways. More interestingly, and we don't really know why this is theoretically, the number of Markov equivalence class or patterns among a set of variables is the number of DAGs divided by 3.7. Right? So we've established this in many simulations, and as I said, we don't really have a theoretical reason for this or a mathematical property of it. So if any one of you would like to work on that and prove it, that's a paper waiting to be published in some arcane mathematical journal. When we have a Markov equivalence class of DAGs with confounders, that's the PAGs. We don't know the complexity of that, but it's certainly large. We don't know the equivalence class size of linear measurement models. We don't know it of directed graphs and confounders. So there's many open questions, but in almost all these cases, the number of objects we're searching for grows at least exponentially with the number of variables, and so doing a search that's really efficient is completely crucial. Okay, so I think a general way to understand this topic in the most general foundational way is really looking at search as a method, right? And there's several things that go into the method that we can vary or change or theorize about in a multitude of ways. But fundamentally, you always are going to be collecting data, right, with some experimental method. And the first thing, right, that you want to talk about in that context is which of your variables you're just going to observe and which you're going to experimentally manipulate, right? So in most of the cases I've been sort of talking about, except for the charitable giving, all the variables are passively observed. But in some cases, like the charitable giving, some of the variables, usually at least one, right, is randomized or applied with a soft intervention. And so we have to at least separate the variables that we're looking at into those that are observed and those that are manipulated. And then the ones that are manipulated, we have to put a probability distribution on, right? In the extremal case, we're just doing a single value, and in most randomized cases, we're doing some uniform distribution over the different ways we could randomize a variable. So that's the probability of the manipulated variables, right? So those two things, sort of at the minimal level, characterize the experimental setup. And then we have data that we get from that setup. And then we have to make a statistical inference, right, from the data we observe in the sample to what is the population from which that data was drawn. So in some sense, the population was created by our choices about what to manipulate and what to observe and what to put on the probability for the manipulation guys, right? But we still have to make an inference from the data about what that probability distribution is in the population, right? We only get to know some of it because we've set that. We know the probability distribution of the manipulated variables because we set that as a randomizer, but we don't know it of the observed variables. So we have to make an inference statistically about what the manipulated distribution is over the variables. And then we have to make a bunch of general assumptions, right? So I've given you the Markov assumption. I'm going to give you faithfulness in a minute because it's a really important assumption. Linearity, you might assume, you might not. Gaussianity, you might assume, you might not. Acyclicity, you might assume, you might not. All of those are important to be clear about. And then you have to actually have some background knowledge, right? So you might say salary can't cause gender, gender can cause salary, right? You might say infection can cause symptoms, symptoms can cause infection. And all those come together as inputs into a discovery algorithm. And then the discovery algorithm is going to output some causal knowledge. For example, it might give you a Markov equivalence class of graphs of the sort I've been showing you this morning that's a pattern, right? But this is the sort of the general picture of causal discovery as a method. So what we've studied, right, is a variety of different situations here, starting with nothing is manipulated and everything is observed, to, right, you can manipulate things one at a time, to you can manipulate simultaneously lots of variables independently, right, to you can manipulate things with a hard intervention or a soft intervention, right? So there's lots of different ways you can think about this, right? And there's lots of different assumptions here, right? I'm going to show you the faithfulness assumption in a minute, and there's many algorithms that do not assume that, many algorithms that do, right? Linearity I've talked about, Gaussianity, acyclicity, all those are, you know, combinations of assumptions you can study and put algorithms in place that are either provably reliable or not and have various kinds of properties, right, when you have finite samples. Okay, so here's an example of one case that I think we've already been over, right? Let's say everything is passively observed and we make statistical inference about independence relationships. Right, so we have a data sample, we make decisions, and then in our inferred population distribution PV, right, we've observed only a single independence is actually true. X1 is independent of X3 given X2. Then our general assumptions are we have the Markov condition, we have faithfulness, and there are no latent variables and no cycles, for example. Then we use a discovery algorithm like the PC or the GES or the FGS, and this is what we come out with as the Markov equivalence class of causal patterns, right? Causal graphs, that's a pattern. And then we add background knowledge that X2 is prior in time, that will have the effect of cutting out one of those members and give us only two members of the equivalence class left to worry about, okay? So this is sort of the case that we went over this morning and you did in the search, but there's many others. Excuse me. Okay, so let me get to the faithfulness assumption here because this is sort of important and you've, without knowing it, you've actually been using this faithfulness assumption, okay? So here's an example, I think, which motivates it, right? The basic assumption says that, right, when we take a causal structure, we ask what prediction does it make about independence, right? Markov and deseparation give us that, right? But it might be the case that there are other things, there are extra independence relations that hold that don't come from the structure prediction through Markov, but just hold by chance, right? And here's an example. So this graph among tax rate, the level of the economy, and the tax revenues the government pulls in, right, is a complete graph. Every edge, every adjacency that could be there is there. So what independence relations does this entail? None. According to this graph, if I apply d-separation or the Markov condition, nothing is entailed, right? So we should observe no independence relations whatsoever according to the Markov condition and the d-separation. But it might be the case, right, that the two mechanisms between tax rate and tax revenues exactly balance. So take them one at a time, right? This says, right, that if we hold the economic level of activity in the country fixed, right, and we raise tax rates, what's going to happen to tax revenues? They go up, right? So beta 1, whatever it is, it's positive. Right? That's, I think, uncontroversial. The tax rate and its effect on the economy is thought to be negative, right? If we have, right, a higher tax rate, right, that's going to inhibit economic activity, and so beta 3 is assumed to be negative, right? The role of the economy in causing tax revenues has to be positive, right? If we fix the tax rate and we increase economic activity, right, that's going to increase tax revenues. So we know that beta 1 is positive, we think that beta 3 is negative, and we know that beta 2 is positive. So this root is going to produce a positive association, and this root a negative association, right? What if they balance exactly and perfectly, right? In which case, tax rate and tax revenues will appear to be uncorrelated, and they'll be independent. They'll look like they're independent, and it won't be because of the structure. It'll be because of this very, very careful and precise canceling of two different pathways that's a parametric coincidence of the highest order, right? So we say that's an unfaithful parameterization, right? And then, in fact, in mathematical terms, this is what would have to happen. Beta 1 would have to be exactly the same as negative beta 3 times beta 2, and by saying it's not going to be exactly the same, that is to assume faithfulness. So we're saying faithfulness is no coincidences like that can actually occur in the world. Now the problem statistically is that even if they're not an exact coincidence in the world, if it's a pretty close coincidence, so it's really close to being balanced, so it doesn't violate faithfulness, it might be difficult to detect that there's an actual correlation statistically. So in some sense, the effect on inference is just as bad if it's a close to faithfulness violation as it is for a full and complete faithfulness violation. So the basic idea, right, is that all and only the constraints that hold in the distribution are entailed by the causal structure, not by the parameter coincidences, which would have to be on some lower dimensional space in order for those things to happen. But I think the better way to think of it is this, right? In the causal Markov assumption, right, if we got two guys that are disconnected, that implies that they're independent. Faithfulness turns that around the other way and says if we got two guys that are independent, that implies they're disconnected. So it's just going both ways, right? So we had the tax rates and tax revenues. If they're independent, we're going to assume that they're causally disconnected. And in the example I showed, they are causally connected, but they balance exactly. So that example violates this assumption. We think there's no way to violate this assumption because there's no parametric way we could produce, right, a violation of that assumption. There is a parametric way to produce it, but it's very unlikely. Okay? So that's the faithfulness assumption. Now the reason I bring it up is because in particular in biomedical discovery, right, it's very, very problematic in certain ways. And let me show you why. So here's a case where by evolution, right, in a certain sense, we're going to have an unfaithful structure. Suppose protein 24 is extremely important for some metabolic basal activity that the body needs to actually accomplish. And because of that, it's got a backup system in case the usual gene that makes protein 24 is knocked out or shut down or defective. Right? So in the usual state of affairs, gene A is expressing and creating protein 24, and if it was to fail, gene B would kick in and, as a backup, produce protein 24. Now, it doesn't make sense for gene B to be doing its thing when gene A is actually working and healthy, right? So there's also this inhibition that gene A does. So when it's active and producing protein 24, it's also inhibiting gene B, right? So gene A inhibits gene B, and gene A produces protein 24. But if gene B is not present, it does not inhibit gene B, and then gene B produces protein 24. So if I said to you, well, what's the relationship between gene A being active and protein 24? So take the two cases. One, gene A is active. Is protein 24 produced? Yes. Case two, gene A is inactive. Is protein 24 produced? Yes. So gene A looks like it's irrelevant to protein 24 on the superficial level, right? If you don't know about this backup mechanism, right, and you just said, oh, gene A's activity and protein 24, they're unrelated. They're uncorrelated, right? You'd fallaciously conclude that gene A has no causal connection to gene 24. So this is a violation of faithfulness that I think is evolved, right, as a design feature of your body. So it's more common in backup mechanisms, at least at a rough level, than we might think. Okay, here's another case that's quite common, and it's not the same, but it's still a worry because of time scales. So we have all these things in our body that are homeostatic regulators, and the classic one is your core temperature, right, with response to the environment. Your body is evolved to purposely make your core body temperature independent of the outside air, right? So if the outside air gets too hot, your body goes into sweating mode to cool itself, and if it's too cold, it goes into burning chemicals mode to heat itself up. And the idea is that, right, whatever the air temperature is in the homeostatic regulator of the body mechanism, these should be totally independent, right, at a certain time scale, right? So if I measure, right, the air temperature fluctuations, and I measure your body temperature fluctuations every 5 seconds, right, what will I see? I'll see the relationship, right? Because if I put you into a hot room, right, your core temperature is going to respond and heat up, and then your sweating is going to cool it back down, right? So it won't actually come back to its 98.6 target or whatever it is, right, for several minutes. And so I will see that in the data. But if I don't measure every 5 seconds, instead I measure every hour or every 2 hours, I might well not observe any correlation between the outside air temperature and my internal body temperature. So in that case, it's unfaithful at certain time scales, but still faithful at other time scales, right? So it turns out that the time scale at which you measure repeatedly the same thing, very important. And there's a whole theory about that too. Okay. So that's the faithfulness assumption, and many of the search techniques use it, and some don't. The constraint-based searches and the scoring-based searches have this very nice property, which is they're point-wise consistent, which means that if we actually have the assumptions satisfied and the data grows and grows and grows, that will converge with probability 1 to those algorithms outputting the correct equivalence class. That is to say, it will contain the generating model as one of its members. So these algorithms are provably reliable in the sample limit, right? That's not to say that we know a lot about what they do for finite samples. So there's an interesting topic about the difference between an algorithm that's uniformly consistent versus a point-wise consistent one. A uniformly consistent algorithm, right, will have the same long-run asymptotic properties, but also has this nice feature that along the way, right, we can compute confidence intervals and error bounds. So if I say to you, right, I'm going to measure the correlation between two variables, and my job is to say what the population correlation is, right, I can do that, and I can put error bars around that estimate, and the error bars are going to shrink and shrink and shrink and shrink as the sample size goes up. It's not the case with these algorithms that the output is going to get closer and closer and closer and closer and closer to the truth, right, very progressively and very steadily. It might take, right, a quantum leap at the very end of things because some of the relationships that we need to discover, right, don't get uncovered until very, very late in the game. I'm not going to go into that exactly why, but that's a fundamental limitation on the whole paradigm that's tricky to get around. Okay, so excuse me. There's lots of other algorithms for other kinds of models, right? We're not going to have a chance to cover those, but some of them you'll hear about in the breakout sessions, and some of them we can point you to if you're interested in in more advanced topics, right? The one that I think is interesting to at least mention is the what's called lingam, right? Which is when I have linear relationships but non-Gaussian error terms, right? I can do this really clever technique, which gets me, right, not a pattern or an equivalence class that's got many members. It gives me a single DAG. Right? So I can get a single DAG with a. So that means I can even tell, right, if I have just two variables, I can distinguish between these two graphs with just observational data, not doing an experiment. If what I know ahead of time is that whatever the relationship is, it's linear and the error terms are non-Gaussian with skew. Very cool. Okay, so in a score-based search, right, I'm taking data and I'm computing for each of the equivalence classes I might be searching a score that every member of that equivalence class is going to have the same score, right, as you saw before. And so I'm now searching equivalence classes and giving each a score, and sometimes that score, the BIC, the AIC, the Bayes factor score, those can be very, very, very computationally complicated and demanding to compute, and so it's essential to be efficient in doing that, right? And again, if I have background knowledge, I should be able to use it by cutting out in each of the equivalence classes the members that are inconsistent with that background knowledge. Now, what I haven't talked about a lot, but which is sort of an ongoing research project, and which we hope to actually have more to show you about in some future time, is instead of using background knowledge that's sort of qualitative and discrete, of the sort like there's a temporal tier or there's a required or a forbidden edge, it would be great to have background knowledge that was more probabilistic. So if I said, here's a relationship, right, between this gene and cancer that I'm saying I'm 20%, right, likely to actually, my prior degree of belief is 20%, it's there, right, and all the other relationships I'm less or something. So you could put a Bayesian prior, right, over the sorts of causal pieces of knowledge that we really actually think we have, and then get on the other side a Bayesian posterior about the graph or the causal situation with an equivalence class. That might be very helpful. We don't have anything to offer in the software to that yet, but that hopefully will be there somewhat soon. Okay, so then I was going to show you the lead and IQ search, but let me come back to that. But the basic idea is, right, in the lead and IQ case, the children's IQ is endogenous. It was, right, is the only thing that's measured about the child except for their lead. And the lead exposure we know is prior to the IQ that was measured. So we know that we can put CIQ in the final tier and everything else before it. And we can do a pattern search. And it's really interesting to see actually what you get out of the lead and IQ search. Right? Okay, let me ask if there's any other questions before I dive into deseparation, which is just more fun than you'll ever have. Yeah.
We are using score-based research. How about using people like these values in the data set? Is that just scores, your values research?
Most of the searches, if not all of them, require the data to be without missing values. Right? Now, we have a facility in the program which I haven't showed you, right, but that allows you to complete the data set by imputing the missing values. Okay, so if I take a data set, right, like this, and I put another data manipulation box there, and I run the data into that, and I open that up, the options, right, allow me to discretize the data if it's continuous, convert numerical to continuous, expand cases, calculate, and then, right, they also allow me to do all sorts of things with missing values. I can remove cases with missing values, so I only allow rows which I have complete data for, right? I can replace missing values with my column mode, my column mean, right? I can replace the missing values with the regression prediction of what that missing value would be if I had the other, right, models, et cetera. And I can replace them with random values, et cetera, et cetera. So I really have a lot of options for completing the data, which turn out to be, you know, very useful. Joe, is there anything else I should say about missing data?
It's a huge subject. I mean, there are lots and lots of ways to do it. Maybe one of the things you could do is if you have your, if you come up with a way to do it that you think is suitable to your data in some other package, and go to that package and compute the missing data in that package, and then bring it back to Tetra and analyze it. Because there's just no way to implement all the different ways of computing missing data.
Right, do any of the algorithms do computations?
You can figure out, I forget the name of the algorithm, you can figure out which group it's closest to by doing a clustering search, for instance. In Tetra, we don't have that.
So, in the school-based search, how do we know the search algorithm covered all the model space?
So we guess it probably doesn't, because it's got to be greedy to a certain extent to actually even cover some chunk of the space. So what usually happens is we start out by doing a constraint-based search to get us a starting point. So we do a constraint-based search, that's very fast, and we get a starting point, which is a pattern or a PAG. And then in that pattern, right, we have a score. And then we do, right, all the perturbations that are minimal from that pattern, and then calculate those scores, right, and then follow a certain number of those branches, right, and do a parallel set of searches, right. And then what we've done is a lot of simulation studies to see if we've actually missed, right, the global optima. And actually it's pretty, I mean, you want to describe those, Joe, but it's pretty reliable that we don't. When we do a score-based search, right, what's the worry about finding a local optima as opposed to the global optima? Because we can't search the whole space.
You can't search the whole space. You can get into a local optimum, obviously. Although the way that FGS is doing it, it's less likely to get into a local optimum because it's not actually searching the space using a minimization technique. It's actually looking at it by scoring various perturbations of patterns, as Richard was saying.
Okay. Yeah.
One more related. If we do the searching, say, organization searching for 2 different times, would that give us similar results or give us different results?
So I think the question is, we do multiple searches, right, using different, what would be different about the searches at different times? Right, so we do searches at different initial values. We start things. Would the results be different? Sometimes, yes. It depends entirely on the example. Most of the examples that we simulate from, no, they end up getting the right answer, both times, several times. But if you move some of the parameters that guide the search, like the depth of the search, or the decision cutoff, or the complexity penalty, you can get very different answers. Right, even from the same data. Yeah.
AIC and BIC are measures of statistical risk, but generally, like in machine learning, people will use cross-validation. Would it ever be reasonable to use a method like that here?
Yeah, you can use cross-validation. So we can take data sets we've had, right, split them into a test and training set, right, and then do model search on the training set, and then test that model on the test set. So what that gives you is, it's a little complicated to interpret some of the statistics, right, about model search if you've searched and then tested on the same data set. So what we found is that you don't really get any better answers by splitting the data set, but in some sense, if you want to get a statistic that tells you how likely your model is, right, then that's more reliable if you split the data and do cross-validation. Yeah.
If you replace missing data values with regression predictions, is that just a conditional mean or is there noise to that?
Just a conditional mean. Yeah,
That's in Tetrad, replace them with regression predictions.
yeah, he was asking
Yeah,
whether that gives you a conditional mean or is it add noise, and it's just a conditional mean. It's just a regression prediction.
Questions? One question is Tetrad also include the data to see if you are algorithm.
I'm sorry, I didn't hear that.
In Tetrad, can you have a way to automatically, say, run through another model, see if you determine the data each time to see if you are an algorithm?
Oh, that's a great question. Joe, you want to answer that?
No, but that would be easy to have.
And then, is there a way to run through the different structural coefficients, like if you were to try 0.5 to 2, to see how robust some of your errors are automatically, rather than just,
Yeah, I mean, that sort of thing, that's not in the interface, but that sort of thing, if you just go and grab the code from the repository, you can easily write loops to do whatever you want to do.
So you can do bootstrap sampling, right? So if you want to bootstrap the samples and then for each of the bootstrap samples, run through the algorithm and see what you get, you can do that reasonably well in the interface. It's a little tedious, but you can do it. But yeah, so I mean, what we haven't done, and maybe I'll have Joe show you this tomorrow, is there's a version of Tetrad that's command line. So I'm showing you the version that has a GUI, right? Because it's much easier to teach with it, and I think it's better to understand the basics. But if you're a sophisticated user and you want to actually use the routines and the algorithms, but add your own loops or add your own variants, that's really easy to do. And all the code is available free in GitHub. And the code has a command line interface that allows you to interface with pretty much anything. Or other, yeah.
What validation capacity is available in this test run?
So you can, when you say validation, you mean like simulation studies?
One observation without or k-fold, validation. Because there should be some sort of a validation method that is validating the data.
Can I say, I mean, if you grab the code and look at it, you'll see a whole directory full of tests. So they're unit tests. You're using the JUnit paradigm. And if you just go through them, there's lots and lots of validations of code. So you can just look and see if they have the ones you want. And if you don't have the ones you want, you can just add them.
No, I'm talking about the statistical validation. Including, for example, are we capable to use the leave one observation out and to test?
You can do the leave one out in the interface.
Okay.
Yeah, there's a couple. In general, we have not focused a lot on that. And if you want to take the data offline and do it on whatever package you like, that'd be great.
To my knowledge, there is no package that is capable of this.
Well, you could easily write one because it wouldn't be hard to, write a loop in which you took a sample point out, ran the algorithm, stored the results, etc. Good? Okay. All right, I think I have enough time to get through deseparation. So for those of you who your brain are fried, do email or whatever. But for those of you who want to actually see the innards, here it is. Right? It's not here. I got to get the PowerPoint back up. Okay, deseparation. So there's two notions, one of which you've already learned, which is colliders versus non-colliders, and the other is the idea of an undirected path. And those are the two ideas, right? So undirected paths are any sequence of edges forgetting the direction that start at one variable and end in another, right? So if I'm looking at x and y and that complicated object up above, right, and I say, what are the paths, right? There's several. There's one of them that goes through v, and I notate it as this, x, v, y, where I've put in the arrow directions, right? There's another that's going from x to y as one direct edge, so the path length is 1, right? There's a third that goes through z1, right? There's a fourth that goes x, z1, w, u, y. I put it in red. There's a fifth that goes through x, z1, z2, u, y, right? And there's even a sixth that goes all the way back, right? X, z1, z2, u, w, y. Right? So this graph was picked, so there's a lot of undirected paths. Right? Okay, so this is an illegal path because it loops around, right, and hits the Z1, Z2 edge twice. So an undirected path is any sequence of non-repeating edges that it gets you from one variable to the other. And the idea is extremely simple. If I took out the arrowhead and directions, right, it would just be a way from getting from one to the other spatially and graphically. Okay? So the basic idea of deseparation is some of those undirected paths, right, are going to produce association, and some of them are not. And when you condition on variables, those conditioning variables can block a path from producing association, or they can take a path that was not producing association and activate it so it does produce association. So in deseparation, you have to block every path, right? And if there are any paths that are active and non-blocked, association, right, flows, and otherwise it doesn't. And the key to understanding what paths produce association and what don't is through colliders and non-colliders. So we did that before. Y is a collider on that path, right? Shielded and unshielded, that's review. And a variable is not a collider, it's a collider on a path. So take the variable u, right? You can see that on the path WUY, right, it's a collider, but on the other paths, right, it might be a non-collider. So here's a path Z2UY, right, U is a non-collider, but if it's on the path WUY, right, oh, it's a non-collider as well, so that's a bad example. So what was I looking at? Yes, that's right, good. Right, and that's a collider. So U is a variable, right, that's a non-collider on some paths and a collider on others. So it's just, you just have to keep in mind that when you talk about a variable, it's a collider on a path, right, or a non-collider on a path. It's not all by itself one thing or the other. Okay, so now change gears from the abstractions of the x and y's, and we'll go to a concrete case so you can understand why it is that colliders are so interesting and weird, right? Because they, unlike non-colliders, induce association once I condition on them. So here's the classic example that shows it. If I look at a situation with a car and I say sometimes the car will start and sometimes it won't, and everything works in the car, except perhaps the battery, which might be dead, right, and the gas tank, which might be empty, right, then this graph accurately portrays, right, the causal relations between gas tank being full, the battery being alive or dead, and the car starting, right, with one assumption, which is that the gas tank has no causal influence on the battery and vice versa, and there's no common cause. Now, it might be argued that that people who tend to let their battery go dead are also the people who tend to fail to fill up their car, right? Ignore that for a second. Let's imagine those are completely independent. So let's take this to be an accurate representation of the world. Now, if I said it's an accurate representation of the world, right, what's the relationship between gas being filled and the battery being alive? There's no causal connection, right? Gas doesn't cause battery, battery doesn't cause gas, and there's no common cause. So they are causally disconnected, which means what by the Markov condition? They're independent probabilistically, right? They're probabilistically independent. So gas and battery are independent. And we represent that by, right, that little symbol. Now, the next question is, well, what if we actually knew whether the car started or not, and we conditioned on it? Are the gas and the battery still independent? And the answer is no, right? Especially in the case where the car starts equals no. So you get to observe and be told ahead of time, car won't start. And now the question is, does the state of the gas tank tell you anything about the battery, right? Where it did not before, now it does. The car won't start, you know that, and someone says to you, gas tank is full, what do you know? Battery's dead, right? And that's called explaining away, and it's a very common situation, but it essentially shows you why conditioning on a collider induces association right, that wasn't there ahead of time, right? Now, if I take the same basic undirected structure, so if I had no arrowheads, this would look the same, right? But I have a non-collider, right? It works exactly the opposite. So I have exposure, right, to some disease. Let's say the kids, right, are being brought to the daycare center, and other kids in the daycare center have chickenpox, right? So you are taking your kid to that daycare center, and you're exposing them, right, as opposed to a situation where you hold them home and you say, we're not going to bring you in, you're not going to be exposed. So exposure could be yes or no, and it's quite clear that that's a causal influence on whether you're infected with something like the chickenpox virus. Doesn't determine it, but it certainly makes it more likely. And if you're going to get symptoms of the chickenpox rash, right, that's going to happen only when you're infected, but not always when you're infected. Okay? So that graph, I think, accurately represents the world. And in that graph, right, exposure and symptoms are clearly associated. Right? No question, learning about whether a child has symptoms will tell you about exposure and vice versa. But once I know whether they're infected or not, right, learning that they were exposed tells me nothing extra about whether they have symptoms. So you can see, right, that the undirected structure is the same, but in this case, right, these guys start independent, but become associated when we condition on the middle guy, the collider. And in this case, right, they start out as associated, but they become independent when I condition on a collider. So this asymmetry in the non-collider collider, right, is sort of what drives the whole theory of deseparation and the whole field, really. That's the asymmetry. And this story, right, would be the same if I moved the causal order the other way or if I had a common cause, right? And the common cause example I gave you before was where smoking is a common cause of yellowed fingers and lung cancer, right? Yellowed fingers is, right, associated with lung cancer. It's predictive of it, right? But once I know how much you smoke, it's independent. So once I tell you how much someone smokes, then saying, would you actually like more information about the state of their finger color? You'd say, no, I don't need to know that. It's irrelevant. It's been screened off by the non-collider, which was smoking. So colliders, right, induce association when we condition on them, and non-colliders prevent association. So they act exactly opposite ways. Okay. So what we say is that x and y, right, are deseparated by a set z in a graph, just in case every undirected path between them is made inactive by that set z. So z has to make everybody inactive, so there's no association flowing. That's the first thing. What is it for a path to be active or inactive? Right? An undirected path is inactive relative to that set, just in case any node is inactive. So you can block a path with a single node, making it inactive. It's like every variable on the path has to be active for that path to be active. You can block the path with a single variable, but you can't activate it unless every variable is active. And a node on a path is inactive, and this is where it gets a little complicated, right, is if it's a non-collider that you've conditioned on, or it's a collider that you have not conditioned on, or conditioned on its descendant, which is a big pain. The dual to that is maybe a little bit easier, right? A node is active if it's a non-collider that you've, right, failed to condition on, right? Because that's like symptom. I mean, that's like infection or smoking, or it's a collider, right? That is in the set, so you've conditioned on the collider and therefore activated, or you've conditioned on a descendant, right? So in the car starting example, what would be a descendant of the car starts? Let's say there's smoke coming out of the exhaust, right? And so if I tell you there's no smoke coming out of the exhaust, right, that's going to be just as informative as the car starts or not, and make gas tank and battery associated if you knew whether there was smoke coming out of the exhaust. Okay, so let's apply it to this case, right? And let's ask ourselves first whether x is deseparated from y relative to the z, which is the empty set. So you can condition on nothing and ask, are x and y deseparated or deconnected, which just means are they associated or are they independent? Okay, are x and y deseparated relative to the empty set? Well, what are the undirected paths between x and y? There's one of them, and there's another. There's two undirected paths. One goes through z and w, and one goes through v. And so if we're going to have either of these paths be active, all the nodes have to be active. A node is active if it's a non-collider that we didn't condition on, or if it's a collider that we did condition on, or a descendant that we conditioned on. So what's the set to condition on? It's nothing. There is nothing. So it just comes down to a collider or not. Colliders are inactive, non-colliders are active. So which of these paths are active paths? Is path 1 active? Path 1 is inactive because of Z1 is a collider, and colliders do not, right, are not active unless we condition on them or a descendant of them. So path 1 is inactive. What about path 2? That's active because V is a non-collider. So relative to the empty set, x and y are not deseparated or are said to be deconnected. Okay? So I've already answered that question. Right? Z1 is not active, W is active, so the path is not active. Right? Okay. Okay, so next, do the same question, x and y relative to z, but now z is the set W and Z2. So now it's conditioned on W and Z2. So we go through the same basic activity, right? We list the undirected paths, right? There they are. Then for each path, we ask, is it active or inactive? Okay, so there's the first path. And then we ask ourselves, right, on that path, is Z1 active and is W active? And what's the answer for Z1? It's active, and why is that? Because Z1 is a collider and we've conditioned on a descendant of it. Right? This is the complicated case. Right? Z2 is in the conditioning set. Z1 is the thing at issue. It's a collider, and Z2 is its descendant. And if it's a collider or has a descendant in Z, it's active. So this is the weird case. Right? So Z1 is active on this path relative to this set, which includes Z2. Okay, so Z1 is good. What about W? W is inactive because it's a non-collider which starts out active, but we conditioned on it and blocked it. Okay, so what about the whole path? No. Oh wait, I went too fast. So this one is inactive, but I didn't ask the question about the other path that goes through V. So is the path XVY active or inactive according to this if we condition on W and Z2? It's an active path because V is a non-collider and we did not condition on it. So this, right, is an active path, and so X and Y are not deseparated relative to this set because of the XVY path. Okay, so here's the two interesting cases. I want you to take out your pen and pencil, right, and see if you can solve these two. So on the top, right, the question is, right, are X and Y deseparated given the empty set? And then are X and Y deseparated given Z1? And that's going to come back and inform us in 5 minutes about a really interesting question that sort of I'll stop with at the end of the morning. And then in the second case, which I'll leave to you guys, right, are X and Z2 deseparated given nothing or deseparated given Z1? So answer the first two questions here. Have an answer to the top question? Are x and y d-separated given the empty set? How many people say yes? How many people say no? How many people say don't know? Okay, you're honest. All right. The answer is no. Why? Because there's an active path through Z1. Because Z1 is a non-collider, and if we don't condition on it, it remains active. So x and y are deconnected, which means they're predicted to be associated, right, if we have faithfulness, by that model, conditioning on the empty set. Now, what about if we condition on Z1? How many people say x and y are de-separated by Z1? How many people say they're deconnected? How many people say I don't know? Okay. Turns out the answer is they're deconnected. This is the interesting case. Why are they deconnected? Well, there are two paths between x and y. One of them goes through Z1, and one of them goes through Z1 and Z2. Z1 is a collider on the second path and a non-collider on the first. So Z1 is, right, both things. And if we look at it on this path, it's a non-collider, and therefore if we actually condition on it, it's inactive. So this path is inactive relative to the set Z1. But now look at the other path. It's a collider. So by conditioning on it, it becomes active. We activate it on this path. This guy is a non-collider. We did not condition, so he stays active. So Z, active, active, so they're deconnected. So there's no way to de-separate x and y unless we condition on Z2. Just conditioning on nothing or Z1, it looks to be associated in both contexts. And this is what's really interesting. So I'm going to jump to why that matters because we're sort of out of time. And I wanted to make sure I get to the end. But the answer in this other case is no in both cases as well. And the reason this case is interesting is because this sort of explains why a dream has been defeated, right? You all, I think, understand, right, intuitively, right, why experimental control is so powerful, right? So take a look at this case and imagine that T is out there, but we don't measure it. It's latent. Right? It doesn't get to be observed, and so we can't condition on it, we can't look at it, it's just completely hidden from us. And our question is there any direct relationship between x1 and x3? So the choices are x1 has only an indirect influence on x3, as I've drawn it up here, or maybe there's also a direct relationship that x1 causes x3 in a way that does not go through x2. So intuitively, if I asked you that question and you could do anything you want, how would you actually establish whether or not x1 had a direct influence on x3 or only went through x2? What would you do? You get to wiggle, clamp, anything you want.
I do a hard intervention on H2.
Yes. I clamp x2 fixed. Intuitively. Clamp it fixed. Hold it down. Hold it still. No variation in x2. I get to clamp it. Wiggle x1. See what happens to x3, right? If there's a direct cause from x1 to x3, which is not in this picture, right, I can clamp x2 all I want, but if I wiggle x1, I'm going to wiggle x3 in some way. So that's the wiggle and clamp theory, right, which is kind of the way everybody actually thinks in the end, right? So if I could experimentally go in and do a hard intervention on x2, I could answer this question, right? So that picture is experimental control. I'm experimentally controlling x2, right? And then seeing if x1 and x3 are still related after I do so. Right? That's the idea of experimental control. Now, I might not be able to do that in this situation and many others. And the dream always was, well, if I can't do experimental control, then I can do statistical control. I could control for a variable and variation statistically, right, with regression, with other techniques, right, controlling for, right? You've all read in the paper 50,000 times, right? And it turns out it doesn't work. They're not the same thing, and deseparation tells you why, right? So, okay, so the truth is, no, it doesn't mediate. No, it doesn't directly cause it. X2 does mediate, right? And how to find it out? Well, we first, let's say, experimentally control for X2, and we do that with a hard intervention, just as you suggested. So we put this I in place that actually controls X2, right? That eliminates the influence of X1 and T, right? And in the resulting graph, right, X3 and X1 are deseparated by the X2 being set variable, because that is the resulting graph, and there's no connection of any sort left over between X1 and X3. So they look independent. Right. That's the resulting independence relationship that we could measure in the data were we to be able to do a hard intervention on X2. Now take the same system and say we can't do any interventions, all we can do is statistically control it, right? And that is the same as asking, is X3 and X1 deseparated by X2? And you'll recognize this is just the example I had you do, right? And the answer is no. Why? Because this path, right, is active unless we control for X2, so we must statistically control for X2 if we're going to block it. As soon as we control for X2 statistically, we activate this path. And that's what gets us. So there is no way to deseparate X1 and X3 if we don't measure T, because X2 is a non-collider and a collider. So, right, that's the reason that experimental control and statistical control are not the same thing, come apart, which is kind of cool. Okay, it's a couple of minutes of 12. I know you've been extremely patient and very forbearing, and I thank you for that. If you have any questions, happy to answer them, but otherwise, those of you who want to break for lunch can do so. Come back here at 1:30, and we will start the breakout sessions, and you'll be in a whole different space. Yeah?
Yeah, different approaches for the controlling the confounded. Statistical approach or in methodology limiting restriction. If here I just limit the variation of X2 by restriction, what happens to the
Doesn't matter. I still get qualitatively, I still get the connection. So you got to print it completely.
even restriction in this case doesn't help us?
No. Nothing helps. The only thing you can do here is do what's called an instrumental variable estimator, right, with making other assumptions. Yeah, you can treat X1 as an instrument if you actually know something about the structure. Okay.